So hello everyone. We're going to start talking about behavioral patterns in this lecture. So let's introduce what behavioral patterns do in general. So some systems require complex and extremely decoupled relationships. Behavioral patterns like these are used on these tightly interconnected systems so that even though they are interconnected with these multiple classes and multiple relationships, they become easier to maintain. What these patterns do is that they separate behavioral responsibilities among the classes in your system in such a way that volatile behaviors or behaviors that change easily are encapsulated deep into your object structure. The first one that we are gonna implement right here is the strategy pattern. And the strategy pattern, I've talked about this when I introduced design patterns. So some systems require behavior that have to be parameterized for other behavior. And this specific mechanism right here is easily done in functional programming environments since higher order functions are used to represent these. So if you remember when we talked about Haskell, higher order functions are functions that can either accept functions as parameters, return functions as parameters, or both. But we're focusing on one of the aspects of higher order functions here, which is its capability to accept functions as well. So if you're in an environment where you do not have these lambdas right here, and by the way, Python has lambdas, but we're still going to implement the strategy pattern uh, for the for the purposes of implementing it lang. So if you remember, you have a lambda, for example, you're able to pass a lambda into some function as a parameter. And inside that function, it can be used as a function, something like that. So again, parameterizing behavior or passing functions or passing methods in general. So that is easily done in functional programming environments. But in programming languages that don't support these features, the strategy pattern is used. That's the reason why this pattern exists. It's out of necessity. So the solution for this one, so functions that are not first class citizens, what we do here instead, so that they're able to be passed, are encapsulated inside a strategy class. A strategy class simply contains the method execute uh, params. I've included there whatever parameter you might think of adding. So this method right here is a member of the strategy class. So the execute params represents the behavior that you want to be parameterized or passed into a higher order function. So there should be a quotation here because this is not really a higher order function. What you're passing is just the strategy class. So any method that can be passed into a higher order function should realize the strategy class. So this is like the workaround that we're doing for programming languages that don't support parameterizing behavior. So since you cannot pass a function, let's say f right here is some function, since you cannot pass this as a parameter to a higher order function, what you do instead is you encapsulate it in some class. And since instances of classes or objects can be passed as parameters, then you can pass this as parameters to some other function, for example. And inside that, this one, the exact behavior of f right here will be placed inside the execute function. And when you want to call this execute function, all you have to do is to, or sorry, when you want to perform this behavior inside the function that you pass it to, so all you have to do is to call the execute method of f. And it will be like you have passed the function itself. So the workaround here is to package the function into a class, then it can be passed as an object now. So this is what the strategy pattern looks like in a class diagram. So you have here an abstraction called strategy, which contains the abstract method execute. So the exact number of parameters, it depends on you. So pero the number of parameters that are placed here, that are specified in your abstract method execute inside the abstraction strategy, that must be the same as the realizations. So you have here two realizations for the strategy. You have real strategy 1 and real strategy 2. And again, the implementation for execute right here, it should follow the parameters, the type signatures of its parameters and the type signatures of its return. So I haven't written here what it returns. It doesn't, you don't have to return anything in the execute. You can return anything. You should just make sure that the strategies that realize your strategy abstraction should also follow the type signature of whatever you're returning. So considering that, let's say you have a client class right here, and this client class is where your higher order method exists. So your higher order method right here, you will pass the parameters and you will also pass an instance of strategy. So inside your higher order method, all you have to do is to delegate the call or delegate the behavior by invoking the strategies execute function. Strategy, whatever that strategy is, it could be real strategy 1 or real strategy 2. It could be any realization. But higher order method treats it just like any other general strategy. So it will call execute. Oops. And then it will pass the parameters that you want. And that is if you need the parameters to be passed in the higher order method as well. It could also be possible that you don't need the parameters right here. The parameters are somewhere else. It may be generated inside higher order method, for example. So maybe params will be built or will be prepared inside your higher order method's body. So you don't need to pass params anymore. You will that params that will be built inside your higher order method is then passed in your execute function. So the object params right here represents the data that you need to pass into the correct class. In this pattern, you pass the whole strategy realization so that, oops, let me scroll down first, so that strategy.execute params perform the desired behavior. You can add other methods in strategy abstraction if it makes sense for the system. So there can be more things right here inside the strategy abstraction if it makes sense for the system. For some reason, for example, you want this strategy to have a string representation. So you add a string representation for this strategy abstraction so that it may be realized by the realizations for strategy. So it's actually very simple lang, the concept of a strategy pattern. The main idea of this concept is that you're trying to simulate higher order functions. But for some systems who cannot do that, all you have to do is to package the behavior into a method and put that method inside a strategy. And that method will be called execute. Okay, so the example, right? Oh, before we go into the example, let's actually show you a demo of how a general example for this works. So let me discuss what these classes are. Again, you have the abstraction strategy. It contains one abstract method called execute. And for this context, let's say you only pass one parameter here. Okay, so here are your realizations for strategy, real strategy 1 and real strategy 2. So they don't really have complex behavior, they just print something. So I just did that just to differentiate between the two strategies. So the strategy, the realization, real strategy one, its execution will print real strategy one, blah, blah, blah. On the other hand, real strategy two right here, its execution prints real strategy two. And by the way, you haven't seen this syntax before, but I have written this in the guides for extra Pythonic syntaxes. So if you notice, this is a formatted string in Python. This is what you do if you have a lot of concatenations, but I'm using this opportunity right here to show this syntax to you so that you can try using this yourselves as well. And if you notice, this formatted string right here looks very similar to how you format strings in C. So the first part of a formatted string is the string itself. And you'll notice this %s right here. That %s will be replaced by this params right here, which is a string. Or actually, it's not typed right here. But I think the way I'm using it is a string. So whenever you print something that is a string followed by the %operator followed by the parameters, so you have to, so Python will interpret that as a formatted string. It will replace the %s right here with the params right here. And since you're using %s, that refers to a string. So it will treat params as a string. If it is not a string, for example, it is an integer, for example, you'll be using %d for that. Similar to your similar to how C formats strings as well. Just like that. Okay? So don't be surprised about what this syntax does. It's just formatted string. This is very helpful if you have a lot of concatenations in your prints or in the strings that you're returning, for example. Okay, so here's your client, and this is where the higher order method resides in. So it prints parameterized behavior, for example, and the data that you're passing right here, I called it params in the class diagram that I showed you. So this data that you also pass in higher order method will be passed in execute right here, s.execute. And whatever specific strategy realization that you're passing right here, that the behavior of the execute method depends on the exact type of S, this instance of strategy. If you're passing an instance of real strategy 1, then this specific print will be performed. If you're passing if you're passing an instance of real strategy 2, then this specific print will be printed. So outside the class, this is what you're doing. You have here an instance of a client called S, and you're calling its method higher order method, and you're passing foo as a parameter. Let's change the other one into something else so you can see different parameters being passed. Okay, so to demo this, let's run this one right here. Python general example.py. So parameterized behavior, this was printed inside your higher order method. This one right here. In real strategy 1, right here is printed with the parameter foo because for the first higher order method invocation, you're passing an instance of real strategy 1. Okay? And for the second print right here, you have real strategy 2 with the parameter bar because you're passing an instance of real strategy 2. If you notice right here, real strategy 1 is not a function. You might get confused about this one. It is invoking the constructor for real strategy 1, therefore invoking the invisible init that exists right here. And if you remember, I think I talked about this before in the factory method pattern. when you do not specify the underscore underscore init function, Python will automatically do that for you, and the init function will just be an empty init function. If you, again, that's if you don't specify what init function does. So for this specific example right here, since we haven't specified what underscore underscore init does, therefore our init function is just an empty function. Since again, we're not really preparing anything, we're not really adding attributes to it. So right here, real strategy 1, you can replace this with an actual named instance. For example, you can do something like this. Strat1 is annotated as a strategy, but it is specifically a real strategy 1, for example. That's how you instantiate things, right? So I can replace this with an actual named identifier that represents a strategy. So that would be strat1, and it will still work similar to what we did before. There you go. Another thing, again, this data right here, it is possible that you don't need to pass this data which is needed for your execution. It is possible that that data is generated somewhere in your higher order method. So for example, it is generated right here. Data is equal to some number, some string, for example, literal string. And you don't need this data anymore to be passed for your higher order method. So I can delete this, and I can delete these two arguments right here, foo and bar, and just pass some instances of strategies. And if, as you expect, what will be printed as the parameter would be literal string for both of them. Okay? Great. So for the example that you will be implementing for your lab exercise, so fraction calculations. So what you'll be doing is you're creating a less sophisticated version of a fraction calculator. So this calculator that you're implementing only has arithmetic operations inside it. Arithmetic operations meaning addition, subtraction, division, and multiplication. So inside this calculator, a calculation is represented in a calculation instance. Let me replace that. So every calculation has 4 parts. So a calculation instance has 4 attributes. It has the left right here, which is a private attribute, as you notice with the double underscore. So left right here, underscore underscore left, represents the left operand. Fraction, underscore underscore right represents the right operand fraction. Underscore underscore operation represents the operation, and underscore underscore answer represents the solution to this specific operation right here. So left operation, right, what would be the answer that is represented in your answer attribute right here. So Python does indeed support higher order functions, but your boss is anti-functional programming, so let's say he forbids the use of these features. So because of this, you decide to implement the strategy pattern instead. So to do this, you need to create an abstraction called operation. Oh, pero before we move on to the solution, let's take a look at what the current situation of your lab exercise looks like. So I've already have this code prepared for you. So you have accidentally hidden it. So you already have the fraction right here, the class fraction, and you have here the initialization of a fraction. If you want to create an instance of a fraction, all you have to do is to create these two right here. So an instance of a fraction can be created like this. So f is equal to an instance of a fraction. So let me annotate the type of this one. It's a fraction, specifically an instance with a numerator of 1 and denominator of 4, for example. So This one right here represents the fraction 1/4. Again, if I try to print this, f, there you go. And to demo what this looks like, let's zoom this in a little bit. Let's clear everything. Let's clear all the clutters. What was I gonna do? So Python lab exercise fraction calculated at py. There you go. Oops, there's a mistake. Oh, I know the reason for this mistake. It's not supposed to work, because yeah, this is incomplete pa man. One of the lines right here will cause an error when ran since operation does not exist yet, because you will have to implement it. But anyway, I can't demo this broken one, this incomplete code right here. You're going to be the ones to complete this. But anyway, this is how you create instances of fractions. There's also some new syntax that you'll notice right here. There's the use of this special Python function, which is underscore underscore str underscore underscore. So similar to the underscore underscore init function, this is also a special Python function. And the underscore underscore str function should always return a string, and it should always accept nothing but the self lang. So what does the underscore underscore str function, what is it supposed to do? So you should return a string representation of this class or this instance, for example. So if you do this, if you implement the underscore underscore str function for a specific class, then that means that class becomes printable or stringable. So it is printable, meaning you can automatically print it like this, print f right there. And then automatically Python will look for the implementation for the underscore underscore str function inside the fraction class. And if it finds it, then there will be no error, and it will return whatever the underscore underscore str function is returning. Okay? So the same is actually done right here. I'm giving calculation a string representation right there by, again, implementing the special str function, the underscore underscore str function. I forgot to write the annotation for this, but this should return an str right there. And all it returns is the string representation of your calculation. Actually, I have an example. I have here the actual solution for that. Let's take a look at that one. Oops. So here's how your calculation should work. So this is how you create an instance of a calculation. So C right here is an instance of a calculation. So for the constructor of calculation, if you notice right here, it accepts 4 things, not including the self. So the left, which is a fraction, the right, which is another fraction, and the operation right here. So 3 things if you're not including the self di. So again, you can just directly print your calculation C right here because it is printable or it is stringable. So your print C right here will print this calculation. So just to demonstrate this one in code, so Python strategy solution.py. So if you notice right here, the first calculation that's being created, so you're creating an instance of the 1/2 fraction, another instance of a 2/3 fraction, and then an instance of a multiplication operation. So meaning, when you print the calculation, it's going to print 1/2 times 2/3. The answer is 2/6. By the way, you don't have to print the reduced version of the fraction. You don't need to do that. As long as the fraction is correct, the solution to that or the answer to the calculation is correct, then it doesn't have to be reduced. The second one right here, we're printing this calculation instance right here, but we're not storing it into some identifier like this C right here. We're directly printing this new instance. So a new instance of a calculation, but we're passing two named fractions right here, F1 and F2. So F1 is just the 1/3 fraction, F2 is just the 4/5 fraction, and we're passing it the operation called addition. So as you expect, the result that you're going to get is just 1/3 plus 4/5, which is 17/15. Again, the way this is printed right here is decided by the str function that you've created for calculator. Actually, I've created that for calculator right here. This is just a concatenation of left, space, operation, self.right, and then finally self.__ answer. So if you notice right here, for this to work, this str function, again, this is a special call to the __ str function. For this to work, your instances must be stringable. So left is already stringable because we have already implemented the str function for your fraction, right? Right is also a fraction, so it is already stringable as well due to this implementation right here. So for this to work correctly, you must also make the operation stringable as well. And what you need to print for the operations are just the character representation of operations. So for addition, that would be plus. For subtraction, that would be minus. For multiplication, that would be an asterisk. And you also have to concatenate all of that, including an equality right here. And then finally concatenating that with the answer, which is also another fraction. Oops, the rectangles that I drew lined up. So again, this self.__ answer is a fraction as well. So meaning it is also stringable. So meaning this str call right here will work. Again, let me reiterate what this str function does. By implementing this str function right here, you will be making the class itself as stringable and printable, meaning meaning you're providing Python with a string representation of this class. So the string representation of this one is fraction, printed like this, 1 over something like that. Okay, so that's it. So when you try to run this code right here, remember that this is incomplete. So this will cause an error, this specific line right here, since operation does not exist yet. You have to provide that first for this to finally work. And also, the calculation for the operation right here. So this is the parameter that represents the operation. And if you notice right here, answer is currently none. None is basically null in Python. So the answer should be calculated right here. Right now, you can't calculate the answer since you haven't implemented operation paman. So you have to complete this part. You have to fill this with the correct answer. Okay? That is all. Thanks, everyone.